Good evening. Welcome to this talk on backscatter communication and specifically the channel capacity that we get with load modulation in the most general sense. That means no specific alphabet, but we can choose any adaptive passive load termination on our backscatter tag that we can imagine. So a quick primer on backscatter communication. This setup here shows either bistatic BC or ambient BC, depending on whether this electromagnetic field source is dedicated or ambient. It generates an electromagnetic field. This field induces a current in the backscatter tag, and the backscatter tag switches or adapts its load termination in order to affect this current and to affect the electromagnetic field. And this way, information is modulated into the electromagnetic field, which is picked up by the receiver, which can decode the information. And this way, the backscatter tag can transmit information without a transmit amplifier. So just in a passive fashion, which is the charm of backscatter communication. Related setup is here this monostatic backscatter setup, where the information sink is also the electromagnetic field source. And this is well known from RFID and NFC. So what is the state of the art of backscatter communication in terms of achievable rates? So a good start, if you're interested in this topic, is this survey paper here. And these papers here, they look at the channel capacity that you get with a specific modulation scheme and a specific symbol detection scheme of thresholding. So here they have binary load modulation, the same is here with BPSK, QPSK, or 16 QAM alphabets. But we want to take this a step further. We are interested in how far can we go in terms of achievable information rate without specifying a specific modulation scheme. With anything goes in terms of adaptive passive load termination. The contribution specifically of this work is we develop a system model that unifies all the different cases you saw earlier, so bistatic, monostatic, and to unify them in the same mathematical model. Then we study the tag side physical constraints, and we discover that the channel capacity, at least in the non-ambient case, can be described with information theory on peak power constrained channels. And this way we can use existing results and characterize the capacity achieving load statistics and in terms of reflection coefficient and impedance. And in the low-SNR case, we determine that a purely reactive load with Cauchy-distributed load reactance achieves capacity. And we also identify special cases where the capacity result applies to ambient backscatter communication, but not in this talk because of time constraints. So now towards the system model, this is the same picture as earlier. For the bistatic case, we're not doing monostatic because of time constraints, but it's very similar. So here we have the backscatter tag. It has an induced here a circuit description here. This circuit has the tag antenna here with antenna resistance, antenna reactance. Then here we have the receiver circuit with antenna resistance, antenna reactance, and induced voltage due to the electromagnetic field source here at the tag and at the receiver. Then the receiver load is first a reactive element that cancels the antenna reactance, i.e. resonance. And here we have the adaptive load impedance set of n, where n is the symbol time index. So we have a symbol discrete model, and for every symbol, we choose a specific value for this load impedance in order to transmit a symbol. The receive side circuit has now this induced voltage, which is due to the tag current here. And this tag current is affected by the load impedance and is due to the induced voltage here. Otherwise, without this induced voltage, there would be no activity at the tag. Furthermore, we have thermal noise at the receiver here with this Gaussian model here. And the received signal is the voltage here, the antenna voltage. All right, let's look at the mathematics, so just at the cornerstones to appreciate what's going on here. So here is the same circuit again. Remember, with a simple discrete model, we modulate symbols by adapting this load impedance here. And load impedance is a complex number. And for a passive element, it has to have a positive real part, positive resistance. And an equivalent description is the load reflection coefficient, which is crucial for this work here. So you probably remember this formula from your bachelor studies. And here we have the reference impedance chosen to be the antenna resistance, not so important. And I'm sure you remember from the Smith chart that the reflection coefficient of a passive element has to be on the unit disk, on the complex unit disk. And this is crucial in this work here. Now, let's look at the received signal here. This voltage here is just the sum of these voltages here, very simple Kirchhoff application. And you see here, this is missing an N, that here we have the received signal as a function of the tag current here, which is a function of the impedance here. And we can formulate this current given the voltage here that is induced at the tag divided by the serial impedance here of the circuit, which is just RT plus the load impedance here. And we can rearrange this to have this affine expression of the load reflection coefficient, which is super important here. And in terms of received processing, we do the following to obtain a more simple model. We look at this interference cancellation step here. So we subtract this voltage here from the received voltage. This is a bit controversial, but if it's a dedicated EM source, then it's simple. This is just a constant phasor. In the ambient case, you have to decode and subtract afterwards. Also, we look at a certain signal transformation, which seems a bit arbitrary now, but makes things a lot easier. So it's repeated here. And furthermore, we define the signal to noise ratio in this sense here. And with these two definitions here, we obtain a much simpler signal and noise model than we would otherwise. We have a observed signal at the receiver y of n, which is given just by the load reflection coefficient plus additive white Gaussian noise with variance 1 over SNR. And this is now almost applicable to information theory, but we are missing the constraints on the transmit side. Actually, we have already discussed them. So for every simple time index n, the load reflection coefficient has to be on the unit disk. That means the absolute value has to be less or equal 1. And this has the character of a peak power constraint. So it's not physical power, but that doesn't matter from a mathematical perspective. It's the same as a peak power constraint. And so we can enter the world of information theory now. We have this model here in terms of random variables, and we identify it as a peak power limited quadrature Gaussian channel, which in the non-ambient case has fixed SNR. So we can discuss the mutual information between the transmit signal and the received signal. As you know, the difference, this is just as a reminder, I'm sure you know this, as a difference between received signal entropy and noise entropy, because it's an additive channel and because it's Gaussian, we have this expression here, and entropy is defined as follows, and received signal PDF is the transmit signal PDF convoluted by the noise PDF. The mutual information is a measure of the achievable information rate, which can be achieved with error-correct encoding with very long blocks. And the constraint with the unit disk means that the PDF of the transmit signal must be 0 outside the unit disk. So what is the channel capacity in this case? So we have to find the PDF which maximizes the mutual information subject to this constraint. Fortunately, this has been solved quite a long time ago by Shamai Bar-David in 1995. And I will just give you the quick version here. So they figured out that the PDF is supported on a finite number of concentric circles in the complex plane inside the unit disk. The unit circle is always a part of it. So we have concentric circles, uniformly distributed phase on every circle. And you have to determine the circle radii, the circle probabilities, and the number of circles with numerical optimization. And instead of talking about the details here much, I will just show you some visuals. So this is an intensity plot, but you don't see that here because it's constant, of the PDF of the load reflection coefficient. And you see for low SNR, it is supported only on the unit circle. That means we do phase shift keying. Phase shift keying with an infinite number of constellation points. When the SNR rises, we get more circles. Here we have 4 circles. They emerge at 0 and grow. Here we have 6 circles. Here we have a lot of circles. And you see this converges basically to a uniform distribution on the unit disk. And to the practitioner, it's interesting to talk also about the impedance statistic, because impedance has relation to lumped elements, you know. And in turn, for the low SNR case, the impedance is purely imaginary. That means we have a purely reactive load. And for a higher SNR, when we get more and more circles, we get more and more circles in the impedance domain, but they are not concentric, and the density is not uniform on these circles. For this case, at low SNR, we can describe the statistics of the reactance in closed form. We find out that we have a Cauchy distribution here of the reactance. So that means when you have a purely reactive load and your reactance has Cauchy distribution, you achieve capacity at low SNR. Quite nice. And this is also the capacity if the constraint would be that the load is always reactive. Then it's the capacity in any case. All right, let's look at some data rates. SNR is a function of channel capacity is a function of SNR, is the blue curve here, and signaling with uniform distribution on the unit circle is the black curve here, the infinite PSK. Here we have the well-known expression log2 1 plus SNR from the average power constraint case, which is actually, which you see from this high SNR asymptote here. At high SNR is 1 nut above our capacity, which is 1.44 bit. The black curve has a pre-log factor of 1/2 because we only use the unit circle. We don't go inside the unit disk. In terms of circuits, that means we just use the load reactance, but we don't add any resistance so we do not enter the unit disk. And that means we throw away basically half the degrees of freedom, so we get a pre-log factor of 1/2. All right, that was a lot of information theory. Now let's look at some practical alphabets. We can get arbitrarily close to the black curve, to the reactive capacity with phase shift keying. So like with 16 PSK, we are very close until we max out at 4 bit per channel use. With 64, we would get closer up until this point here. And so that's nice, but not so satisfying. We want to get closer to capacity, of course. And for that, we have to go inside the unit disk in terms of reflection coefficient. We can do that with QAM, with a large QAM constellation. We get very high data rates, but we are still quite far away from channel capacity. And a much more suitable modulation scheme is amplitude and phase shift keying, which is quite well known from satellites and optical communications. And here you really use the circle nicely. And you have your constellation points on circles like we discussed earlier. So it's very well suited to describe capacity here. But you have to design it for a specific SNR value, and then you can optimize your radii and probabilities like we saw earlier. And you see for practically intents and purposes, we achieve capacity here at 21 dB. Here, another example with a smaller constellation, we achieve capacity here at 15 dB. This is 64 APSK, which looks like this, and the corresponding impedance values look like this here. And you see this would be quite challenging to realize this with a circuit. Now I have to be very quick to wrap this up. We gave the first description of channel capacity of load modulation with a freely adaptive passive impedance. And unfortunately, I have to stop now because of the 15-minute limit. Thank you very much for the attention, and See you around.